about the shape of a random pattern avoiding permutation.
Hey, so thank you. It's always good to be back in Ames and have the opportunity to speak. So my main goal for this talk is to look at this object here, explain what this is, and this is obviously a continuous object, and explain why I'm talking about this continuous object in a discrete mass set R. So the thing that I'm talking about are pattern avoiding permutation. So first I need to say what a pattern and a permutation is. So I always am going to view my
I think I tried them, they looked okay.
Okay. Yeah, there. Okay, so I have a permutation, so sigma in, say, S7, which is 3, 4, 7, 5, 1, 2, 6. This permutation here, and, well, I'm going to write it this way, so what's a pattern? I choose any, so a pattern of length 3 is I choose any 3 indices here. And then I want to look at the relative size. So my permutation is 1 goes to 3, 2 goes to 4, and so on. So the largest here of these 4, 5, and 1, the largest in the range of this subset is here. So this gets a 3, the second largest gets a 2, and the smallest gets a 1. So I call this triple here a 2, 3, 1 pattern. And then I'm interested in a pattern avoiding permutation. So I take any fixed pattern, let's say of length 3, and I want to find all the look at all the permutations which do not have any triple of indices that has that particular pattern. So in particular, for a 3, 2, 1 avoiding permutation, this is one that we're going to look at a lot. If I don't have the pattern 3, 2, 1, that means that I don't have a subsequence which is of length 3 and decreasing. So the longest decreasing subsequence is either 1 or 2. And 1 is not a particularly interesting case, but 2 is a much more interesting case. Okay, so this is what we talk about, what I mean by pattern avoiding permutation. And what sorts of questions do people ask? Well, in any sort of combinatorics talk, the first question that gets asked is, how many of these are there? So if I take any pattern of length 3, 3, 2, 1, or 2, 3, 1, the number of permutations that avoid that pattern in Sn is given by the nth catalog number. So, well, what does that tell me? That tells me that I have lots and lots of bijections. So there's this famous problem in Stanley's enumerative combinatorics book, so I can now find a bijection between the set of 2, 3, 1 avoiding permutations and any of whatever the 112 different things that he has in that one problem that you're supposed to show are all counted by the catalog numbers. And we'll use this. In particular, the thing that we care about are dict paths. So I care. So these are random walk paths of length 2n. So each step either goes up or down by 1. And are always They start at 0, they end at 0. So we have, in particular, we have a bijection between any set of permutations that avoid a pattern of length 3 and dict paths, and that would be very useful. Okay, so let's so here is how I want to think of a permutation that avoids a pattern, the pattern 3, 2, 1. So you can see there's no decreasing subsequence of length 3. Now I want to divide, and so what? I made this into a matrix, and I just have, on this column is I, and that row sigma I, and then I plotted all the points. And now I want to divide the points up into 2 groups, which I labeled as 1s or 2s. And so the points on or above the diagonal are 1, and the points below the diagonal are labeled 2. So it's not quite a canonical labeling. What I do on the diagonal is doesn't really matter. And then I just projected, so this is below the diagonal, and then the numbers on the bottom and on the side are just the projections. So, and now I see that the 2s here form an increasing subsequence, and the 1s form an increasing subsequence here. And so what sorts of questions do people ask about pattern avoiding permutations? So the first one we said was how many of them are there? The next one is what is, so I want to now just look, I want to say how many of them have a fix, an I, and a J. How many have sigma I equal to J? Or I can be, I'm a probabilist usually, not a combinatorialist, so I want to say, I want to think of this as the probability, so I put the uniform distribution on these permutations, and I want to look at the probability that sigma I is equal to sigma J. So this was kind of the first question that I know of in random pattern avoiding permutations, and this was studied by 2 groups of people. So Igor Pak and Sam Miner, and Neil Madras, and Myrna Pevlibar. So they answered this question very exactly for all patterns of length 3. And so they gave very nice asymptotic representations for what these probabilities were. So this was kind of the introduction to the subject. And then, so when I started looking at this, and I should say who my co-authors are. So my co-authors are Eric Slivkin and Doug Rizzolo. So we started looking, and we wanted to ask a different sort of question. We wanted to look at this as a geometric object. So now I want to restrict myself to just these points that are labeled 1 here. And I want to look at this as a function. So I just linearly interpolate by this function here. They're all above the diagonal. So what am I going to do? I'm going to plot the points sigma I, then I'll subtract off the diagonal. So I'll plot the point sigma I, or the I which are labeled 1. And then linearly interpolate. And this gives me a function here. And now I want to see what happens to this function for a typical permutation as n gets large. Well, so I want to be able to compare them, so I kind of want everything to fit on the same scale. And what do I need to do to get everything to fit on the same scale? Well, I need a scale, as n is growing, then the range of these functions is growing, and I want the range to all be the same. So so now I will write f1 of I over n is equal to this. So I scale the x-axis by n, and I also want the y-axis to be comparable. And to get the y-axis to be comparable, I want to divide this by square root. And so now and this gives me a function. And as you can see, well, and this isn't quite the best example, but they generally tend to be, the permutations generally tend to have something really close to this corner and really close to this corner. So if I draw a graph of what this looks like, these points are always on or above the diagonal, so the numerator is always at least 0. So these graphs will look something like, there'll be some curve here. At 0, they're going to be equal to 0, and at 1, they're going to be equal to 1. And we want to know what this looks like. And so our result was, says the scaling limit of a random 3, 2, 1 avoiding permutation is Brownian excursion, which is a Brownian motion conditioned on being 0 at 0, 0 at 1, and non-negative in between. So that's one way of describing the limit. Now, in a discrete math talk, Brownian excursion is not what you're really familiar with, but so there's a theorem due to chi that might be more familiar, and it says the scaling limit of a random. So by random, I just mean I put equal mass on all the permutations, a random dict path, where, again, I do the same scaling. I scale the x-axis linearly, and I scale the x-axis by n, and I scale the y-axis by 1 over square root n. The scaling limit of a dict path is Brownian excursion. So what does this look like? This looks like a random walk, which is conditioned to be 0 at the origin, 0 at the endpoint, and never negative in between. So now I want to look at what happens beneath. And, well, it's easy to see that these permutations are rotationally symmetric. So if I rotate this whole thing about 180 degrees about the center, then I get another 3, 2, 1 avoiding permutation. So the points that are labeled 2 should also become should also be a Brownian excursion, or minus a Brownian excursion when properly scaled. And it turns out, kind of the interesting thing is, I get one Brownian excursion above the diagonal and one below the diagonal. What's the relation between them? And it turns out that they are asymptotically just a reflection. One Brownian excursion is a reflection of the other one. So if I add up the two functions, then if I add up the two functions, the absolute value is going to 0 as n is getting large. And this kind of allows us to say some other pretty interesting things about pattern avoiding permutations. So one question that came up in lunch was about the occurrences of patterns in some type of permutation, some type of random permutation. And we can now say answer questions like how many inversions or 2-1 patterns this is typical 3-2-1 avoiding permutation. And this question was answered by Svante Janssen. So using our theorem, he was able to do this. And what really matters, so if I want a 2-1 pattern, I have here, I've got the diagonal, I've got some Brownian excursion above the diagonal, and my drawings are never any good, and some below the diagonal. I want to know, so I want an inversion that has to be 1 point on the upper path, followed by 1 point on the lower path. And he was able to say, well, I know that there are roughly n over 2 points on the upper path, and then he was able to say the number of, for each point on the upper path, I can see how many points on the lower path correspond to an inversion based on the height, based on this distance away from the diagonal. And since he knew how many, what the distribution of these away from the diagonal was, he could represent this in terms of the distribution in terms of the distribution of some integral of Brownian excursion. And this works not just for 2-1 patterns in a 3-2-1, but it works for an arbitrary pattern in an arbitrary permutation that avoids a pattern of length 3. So he was able to do that based on our theorems that said what the shape of these 3-2-1 avoiding permutations are. And so now, moving on from this, what I want to do now is I want to look at patterns of length longer than 3 and permutations that avoid a pattern of length 4. And now these aren't so easy to count. Really the only ones, or the main one that can be counted is, not the only one, are permutations that avoid the pattern d minus 1, d minus 2 through 1. That's one of the main groups that has been enumerated. And this is what I'm going to talk about for the rest of the time. So permutations that avoid the pattern k plus 1, k, down to 2 and 1. And in my pictures, k is always going to be 3. So I'll always avoid the pattern 4, 3, 2, 1. But there's no difference between the, whereas there's a huge difference between going from the permutations that avoid the pattern 3, 2, 1 to permutations that avoid the pattern 4, 3, 2, 1. There's no difference going from 4, 3, 2, 1 to a million, and the permutations that avoid the pattern 1,999,999 all the way down. So these are permutations that have longest decreasing subsequence length 3. So longest decreasing subsequence length less than or equal to k. So here I plotted one, and I colored them. So in the 3, 2, 1 avoiding permutation, I divided the indices up into 2 categories. Now I'm going to divide the indices up into 3 categories. How am I going to do this? I'm going to do this as follows. So I label all these green dots 1, and these are all dots such that if I look to the northwest of them, it's empty. So if I take any green dot here, and I look and see what's in the northwest quadrant of that, it's empty. So those are my green dots, and these all get labeled 1. So when I project onto the 2 axes, I get 1. Now I throw away the green dots, and I take the red dots. And the red dots are the ones that only, if I look to the northwest, I only see green dots. There has to be at least 1 green dot, otherwise, for the red dots, there's always at least 1 green dot, otherwise it would have been colored green itself. But these are the ones that see to the west, to the northwest of them, they only had dots that were colored green in the previous round, and then the blue dots are the ones that are labeled 3, and those are the remaining ones. And the ones to the 3 also have the property that nothing to the southeast of them has any. To the southeast of them, it's all empty. So I partition all of the indices into these 3 groups, and it's not too hard to convince yourself that restricted to 1 color, I get increasing sequences. So this gives me 3 increasing subsequences here. It's not quite canonical, because if I would have started by constructing the blue dots first, then perhaps I could have relabeled some of them. But that difference doesn't really matter. It's equivalent to what we did on the previous one, on the 3, 2, 1 avoiding, with the points on the diagonal could be labeled either 1 or 2. There are some points here that could be labeled either 1 or 2 or 2 or 3. But it's almost canonical partition of the indices into 3 sets. Now I want to try and think, what is going to be the limiting object? So that's the main question that I want to ask. So first, are there any, before we get into that, let's stop. Are there any questions about how I take a 3, 2, 1 avoiding permutation and break it up into these sets?
Is it that every single get labeled that the blue will not have, if it has an inversion, then there will be a pattern of like 4?
It
needs a little something.
It needs a little something, but if you get bored during the rest of the talk, you ought to be able to finish this finish the proof of that at the end of the talk yourself. Yeah, so you always, everything always gets one of these labels. These sequences are always these subsequences are always increasing. Now, so now I want to think, what is this? Well, I can do the same, what is this scaling limit of this going to be? I can do the same thing I did before. Take the points that are labeled 1, subtract off the diagonal, scale the x-axis by n, scale the y-axis by square root n. And I can do the same for the reds and the blues. And now I get, so now, do I have the right colors? Red, blue, and I had a green somewhere. Here, so when we do this, we're going to see I get some green path on top. And then the middle ones were the reds. And I get something like this. And the bottom ones are the blues. And I get, so I subtract off the diagonal and then scale properly and linearly interpolate, and I get 3 functions here, where I always have the green on top, red in the middle, blue in the bottom. And I want to try and think what this object might be.
Did they sum to 0?
Okay, so that's a good thing. I wasn't going to do that, but yes, you said previously, or I said previously, that the 2 functions in the last case sum to 0. Here, these 3 functions will sum to 0. So but now I want to just say another way that I can describe a triple of functions such that they're ordered. Such that they start at 0, they end at 0, and they're ordered. And how am I going to do this? I'm going to do this by constructing a matrix. So I want a matrix M by t going from 0 to 1. And I want 3 paths, so I'm going to choose a 3 by 3 matrix. So I've got x11 of t, x12 of t, and I got to fill all these in. And what do I want? I want the ones on the diagonal. So x, I are going to be Brownian bridges. What does this mean? This means Brownian motion such that x11 of 0 is equal to x11 of 1 is equal to 0. And I should say here, real valued. And off the diagonal, so for I less than j, these are going to be complex valued Brownian bridges. And below the diagonal, I want for I greater than j, I want xij to be equal to xji transpose. So what does this do? On the diagonal they were real. Above the diagonal they were complex. below the diagonal they were the transpose. So this is a Hermitian matrix. What do we know about Hermitian matrices? So, tell me when you teach a linear algebra class, what do you tell your students about Hermitian matrices? They have real eigenvalues, so which is good because my functions here are real valued, and so they have three eigenvalues, and they're real valued, and I can call I'll call them lambda 1, lambda 2, and lambda 3. But I have not just one Hermitian matrix, but I've got a whole family of them. So I have gamma 1 of t, which is the largest eigenvalue, so that's bigger than gamma 2 of t, which is bigger than gamma 3 of t. So these are the ranked eigenvalues of the family of matrices M of t. And if I choose, so this gives me a collection of a measure. So I have a measure on the Brownian paths. That gives me a measure on family of matrices, and then that gives me a measure on triples of functions here. So my goal is to show that the scaling limit of the random pattern avoiding permutation that I see here, when I scale it properly, is this what we call here which is a Dyson Brownian motion. Except there's one mistake I've made. So can someone tell me what we've already kind of talked about it? What's the one thing that I haven't talked about yet? So you should know the answer. Yeah, so they sum to, so I want these guys here to sum to 0. So I want my eigenvalues of my random matrices to sum to 0. So how do I get the eigenvalues of the random matrices to sum to 0?
Trace.
Yeah. So the sum of the eigenvalues of the matrix is the trace, the sum along the diagonal. So I want to introduce that the sum I goes from 1 to 3, xii of t is identically 0. So I need that condition as well. Now, how am I? So that's what the main theorem that we have is. Now, so are there any questions about that?
Where do the complex, I mean, I see 3 real functions. Where do the complex functions come into this?
The complex, so they just are the entries of the matrix, but the eigenvalues are real. So they don't show up here at all. Now, okay, so for the last little bit of time I have, I want to talk about how one might prove this theorem. And the kind of standard way, and what we talked about before, was I want some bijection to a nice space. So unfortunately, that's not going to happen. What is the space that I would kind of hope that there would be some nice map to? Well, I've got here, I can think of these as kind of doing random walks, and they're ordered. So I want to kind of think of this as some sort of random walk in what is known as the Weil chamber, or with some perhaps some slight abuse of notation is known as a Biot chamber. So this is the set of points x, y, z in R3 such that x is greater than or equal to y, which is greater than or equal to z. So it's a cone in R3. And I want to have, and I know that if I do a random walk in this cone, so random walk, in this cone, conditioned to start and end at the origin is is Dyson-Brownian motion. And if I throw in the condition that I want this to be on the subspace where x plus y plus z is all equal to 0, then I will get that the limit of this is traceless Dyson-Brownian motion, is the object, is that eigenvalue process we described over there. So this is pretty much, there's a long history of random walks and cones. They're a very nice object. There's a nice harmonic function, so you can analyze these quite easily. So the conditioning, where you might think that the conditioning would be a real nightmare, the fact that you have a harmonic function which is 0 on the boundaries allows a pretty nice analysis of random walks and cones. So this is kind of what our goal is to get to. To get to this, a random walk in this cone here. Now how am I going to do this? I'm going to tell you another way to go from this permutation here to a triple of functions. And what I'm going to do is I'm going to look at these projections, so I have a projection onto the x-axis here, and a projection onto the y-axis here. And so what I'll do is this coordinate here is going to be negative, and this coordinate here is going to be positive. So if I see a 1 and a 3, so the 1 here means I increase the first coordinate by 1, and the 3 here means I decrease the third coordinate by 1. And then I go on 2 and 2, so I increase the second coordinate by 1, and I decrease it by 1, so I don't move anywhere. Then here, I increase the first coordinate by 1, decrease the third coordinate by 1. Now, what happens, it's easy to see that this will force always x plus y plus z to be equal to 0, because I always increased one coordinate by 1, and I always decreased one coordinate by 1. So I started out at 0, and at each time the sum doesn't change. It's also pretty easy to see, since I projected the blues on here, and then over here, I've got the same number of 3's in this sequence as in that sequence. So by time n, I'm going to get back to 0, 0, 0. Now I just hope that they satisfy this condition here. I would be really, really happy. My life over the last 5 years would have been much, much happier if they would have satisfied this condition. But they just don't. And so here is a 3-2-1 or 4-3-2-1 avoiding permutation here. I projected onto the axis. I drew the paths that I got, and they just are not necessarily ordered the way they should be ordered. Why aren't they ordered the way they should be ordered? Well, it turns out because I've got big long streaks of red, followed by big long streaks of blue, followed by big long streaks of red. And this is just not typically the way random walks behave, but it's something that they could do. Random walks by definition, are allowed to do all the possible things. But some properties are much more likely. So if we kind of just throw away the things where I have really strange behavior like this, then it turns out that they are ordered in the right way. And so our goal is to do, so I want to look at this walk here. So I want to project onto the axes and look at this walk here. And I want to say that the distribution of these triples of functions I get from this random walk is really close to what I get by doing the appropriate random walk on this space here. So that's one thing that I want to say. And then the second thing I want to say is I had two functions that I got from my permutation here. So one was I projected and I drew this way, and the other was I just did the linear interpolation. I plotted the points and did the linear interpolation. I want to say that these two are close, so that for most permutations, these are close. And again, it's going to be exactly the same thing. I want to say, well, if the arrangement of greens, reds, and blues when I project onto this axis is the same as when I project onto that axis, and if they're roughly well distributed, as the vast majority of random walks will be, then the two functions that I get are pretty close. And that allows me to say that the distribution of these functions here is converging to the traceless Dyson-Brownian motion, and the distribution of the functions I talked about earlier is also converging to the traceless Dyson-Brownian motion. And so that is kind of what we've done, and hopefully will be appearing on the archive in the next week or so. And but then some of the other questions that we asked before about, you can ask questions about, I didn't talk about this earlier, about fixed points, about the number of involutions, about all these sorts of things. Presumably we have this shape theorem, we have this technology that Svante Janssen did with our previous work. Presumably this is the sort of question that could be answered about the permutations that avoid these longer patterns. So that's kind of where we hope to go in the future.
Questions?
Yeah?
So you mentioned that with, let's say 3-2-1 avoiding permutations or 4-3-2-1 avoiding permutations, that you know what the expected number of inversions there are?
Yeah.
Do you expect, and it's concentrated, I assume?
Yeah, it's so I mean, it's going to be, I mean, for inversions, I mean, it's going to be it's going to be some subset of n squared, because they're most n squared points. But it turns out that it's on the order of n to the 3 halves. So you take the number of inversions, you divide by n to the 3 halves, and plot that. That gives you some distribution, and that distribution will be the same as the distribution of some integral over Brownian excursion. Oh,
okay, so there's not a lot of inversions.
So it's n to the 3 halves out of the n squared possible. So in general, the theory is there's always some power of n, and the number of these things is n to some power. You divide the number by n to the appropriate power, and you get a distribution, and it has the same distribution in the limit as some integral of Brownian excursion.
Is it like 1 minus 1 over k is the exponent or something like that?
Well, I shouldn't say that much because I haven't really looked at Svante's paper. But it's for every pattern you write down a different function for the exponent.
Okay.
the very first slide, is it the permutation for some bigger k?
Oh yeah, so the very first, so let's go back. So here, what we did, so this is for d is equal to 6. So this is the, well, I'm not sure how this got sampled, but either we sampled a permutation that avoids the pattern 7654321, and then did the appropriate things, or we just simulated the random matrices and plotted the eigenvalues. And my co-authors take care of all our pictures, so I really have no idea how these were generated.
More questions? So let's thank Chris again.